Demystifying LLM Tokenization. What is tokenization? Tokenization is the process of breaking down a continuous piece of text into smaller units called tokens. It's the first step in the LLM pipeline, converting human-readable text into a numerical format that the model can understand. The problem: LLMs can't directly process raw text. They need a numerical representation. Each token is assigned a unique integer ID from the model's vocabulary. Alright, everyone, let's start with a challenge. Imagine your best friend is a robot, but it only understands numbers. How do you teach it to understand human language? Take a sentence, any sentence you want. How about we put one up on the board? Okay, here's our sentence. The quick brown fox jumps over the lazy dog. Now, you are the language to number translator. What's the first thing you do? Do you give a number to the whole sentence? Or do you break it up? What if the robot has never seen the word jumps before? What about jumped and jumping? Are those the same? This is the fundamental problem that we, as humans, solve effortlessly, but it's a massive challenge for an AI. And the solution is tokenization. What is tokenization? At its core, tokenization is just the process of breaking down a big piece of text into smaller, manageable chunks called tokens. Think of it as chopping a salad into bite-sized pieces. An LLM can't eat the whole sentence at once. It needs those smaller pieces, which we can then assign a unique number to. This number is the key. Every word, or part of a word, in an LLM's vocabulary has its own unique ID. So, when the LLM sees the word cat, it's really just seeing the number 1, 2, 3, 4. The word dog might be 5, 6, 7, 8, it's all just math. The three flavors of tokenization. Tokenization isn't a one-size-fits-all solution. There are three main approaches, each with pros and cons. First, there's word-based tokenization. This is the most intuitive. You just split the sentence wherever you see a space or punctuation. The quick brown fox becomes 4 tokens, the quick, brown, and fox. Simple, right? But what about a word the model has never seen? Like, say, frobnicate. To the model, that's a complete mystery. It has no idea what it is. It's an out-of-vocabulary word, and the model essentially has to ignore it. Next, we have character-based tokenization. This is the opposite extreme. You just break everything down into individual characters. THE space QUICK. This solves the new word problem because every possible word is just a combination of characters. The problem? A simple sentence becomes a huge string of tokens, making it incredibly slow and computationally expensive for the model to process. So, we need a balance. And that brings us to the most popular method used by modern LLMs, subword tokenization. The subword solution or byte pair encoding, BPE, subword tokenization is the best of both worlds. It breaks down a text into meaningful subunits. Think of a word like tokenization. A subword tokenizer might break it into 2 pieces, token and ization. The ization part is a common ending for many words. The most common way to do this is with something called byte pair encoding, or BPE. Don't worry about the complex name, the concept is simple. The BPE algorithm is like a smart little linguist. It looks at a huge amount of text and finds the most common pairs of characters. For example, it might find that T and H almost always appear together. So, it says, hey, let's make a new token called TH. Then it finds that T, H, and E are super common, so it creates word, the. It keeps doing this, building a vocabulary of the most frequent words and word parts, giving it a vocabulary that is both flexible and efficient. So, to wrap up, tokenization is the absolutely critical first step in making human language understandable to an AI. It's the process of turning sentences into numbers, and it's what allows LLMs to process information efficiently without getting lost in new words. But what happens after a text is turned into a list of numbers? That's what we'll talk about next. We'll explore how those numbers get turned into rich, meaningful representations called embeddings and how they power the incredible transformer architecture that underpins models like ChatGPT and Gemini.